Imagine for a moment, you're Isaac Newton, okay? Back in the late 17th century. You've just given the world this law of universal gravitation. I mean, a truly monumental achievement. It describes with breathtaking accuracy why apples fall down and why planets go around the sun. It works. It's incredibly precise. But despite this huge triumph, there's this persistent, nagging question, right? A piece of the puzzle that just doesn't sit right in your, brilliant mind. How does the sun pull on the Earth across all that vast, seemingly empty space with nothing connecting them? How can there be an instantaneous pull across such a huge void? And look, this isn't just some simple science question. It's actually a really deep philosophical puzzle about how things interact, at their most fundamental level. And the quest to answer that leads us directly to one of the most profound, most transformative ideas in all of science, the concept of the field. Welcome to the Deep Dive. This is where we unpack complex ideas, hopefully give you those genuine aha moments. Today we're taking a truly mind-bending journey, tracing the evolution of this field concept. We'll follow its path from what was, initially seen almost as like a clever mathematical trick, maybe, designed to escape a philosophical paradox, all the way to becoming what we now understand as the fundamental substance of pretty much all matter and energy in the universe. This isn't just a history lesson. It's really a story that reveals the very fabric of reality. So get ready for a story driven by incredible intuition, flashes of mathematical genius, and some really radical shifts in how humanity understands existence itself. We'll explore how this idea developed, why it matters so much, even in our daily lives, and what it tells you about the universe you inhabit every single day. This deep dive, it's going to illuminate the stark, really fascinating differences between how we used to think about reality and how we understand it today, especially as we move from classical fields to the, astonishing realm of quantum fields. It's a journey designed not just to inform you, but hopefully to genuinely surprise you with how strange and how wonderful reality truly is just beneath the surface. Okay, let's unpack this then, starting with Newton. Here we have this true titan of science, giving us the law of universal gravitation. This was a huge triumph of mathematical physics, right? Describing with incredible accuracy how massive bodies attract one another. It was a formula that just worked beautifully. It allowed us to predict the motion of planets, comets, objects with unprecedented precision. We could literally map the heavens. But as we touched on, there was something that genuinely bothered him, a fundamental how that just remains stubbornly unanswered.
It's quite fascinating, actually, because Newton himself was profoundly uncomfortable with this whole idea of action at a distance. While he had brilliantly described what gravity did, how much force was exerted, how it dropped off with distance, he just couldn't explain how it did it. Think about it for a second. How could the sun, this colossal object, millions and millions of miles away, exert an instantaneous pull on Earth across what looked like a completely empty space? I mean, if you push a cart, you touch it. If the Earth orbits the sun, what's touching the Earth? To Newton, this felt occult, almost like magic, and philosophically it was really untenable for him. It sort of smacked of supernatural intervention, which he, as a scientist, absolutely wanted to avoid. He famously stated in Latin, hypotheses non fingo, which basically translates to, I frame no hypotheses, or maybe I don't do hypotheses. And this wasn't just him being modest, it was a core philosophical stance. He believed physics should stick to describing what you can observe, mathematically precise laws, not delve into unseen, unproven causes or these speculative mechanisms. There wasn't any empirical evidence. So while he could predict exactly where the apple would fall or where the moon would be in its orbit, the magic of the pull across empty space, well, that remained a profound unease. He consciously chose not to guess about it, leaving this massive conceptual gap for future generations to grapple with. And for nearly 2 centuries, physics just had to live with this pretty significant conceptual discomfort. It was like this giant, silent elephant in the room of classical mechanics, a persistent whisper of mystery right underneath the grand structure of his universal laws.
And it really does challenge common sense, doesn't it? I mean, think about our everyday experience. If you want to push a door open, you have to physically touch it, yeah? You apply a direct local force. So how could a distant object push or pull another without any physical connection, without touching it in any way, shape, or form? This fundamental question, this seemingly simple logical leap, it really sets the stage for a massive breakthrough in how we understand reality itself. It forces us to ask, what is between the sun and the earth if it isn't just nothing? Okay, so the first real conceptual leap in solving this puzzle didn't actually come from a theoretical mathematician, locked away with equations and abstract thoughts. It came from a brilliant experimentalist, Michael Faraday, back in the 1830s. Faraday was largely self-taught, came from quite humble beginnings, and he had this completely different, much more intuitive way of looking at things. It involved getting his hands dirty in the lab. He wasn't really a master of complex math, but boy, did he have an unparalleled physical intuition.
Indeed, Faraday was just deeply immersed in studying electricity and magnetism. At the time, people saw them as somewhat separate phenomena, mostly. He had this remarkable insight while doing his meticulous experiments, especially with magnets. He started to visualize the space around magnets and electric charges as being filled with these invisible lines of force.
Nah.
You know that classic experiment, right, where you sprinkle iron filings onto a card held over a magnet?
Oh yeah, the patterns they make.
Exactly. They don't just scatter randomly. They trace out these elegant curving patterns, almost like there's an invisible blueprint guiding them. Now, to Faraday, these weren't just illustrative diagrams or, a neat trick for a science fair. He believed they were actual, tangible evidence of physical state of the space itself. He proposed that the magnet or the electric charge didn't directly pull on a distant object. Instead, it modified the space immediately around it, creating what he called a field of influence. Then a second object, like an iron filing or maybe another magnet, wouldn't interact directly with the distant source. Oh, no. It would interact directly with this field right at its own local position. And this just elegantly solved the problem of action at a distance. Forces in this new view became local interactions between an object and the field present right at its own point in space. It's subtle, but it's a profoundly important shift. It transforms space from just being a passive backdrop into an active participant in physical interactions.
That's a truly revolutionary idea. So instead of this direct kind of mysterious pull from way over there, we now have a local interaction with something in the space, something invisible but real. How did that immediate conceptual shift impact how physicists even approach problems after Faraday? Did it unlock new ways of thinking, maybe beyond just gravity and magnetism? And given Faraday's lack of advanced mathematical training, was there skepticism initially about his non-mathematical, more intuitive approach?
That's a crucial point. And yes, initially there was indeed some skepticism, especially from the more, let's say, mathematically inclined physicists of the time. Faraday's ideas were expressed through these really detailed experimental descriptions and conceptual drawings, not abstract equations, which wasn't the usual way. But his experimental results were just so compelling and his intuition so profound that it kind of forced people to consider his radical view. It provided a framework, a way of thinking about all sorts of non-contact forces, not just magnetism. Instead of just describing what happened, physicists now had a way to conceptualize the mechanism, the how, even if it was invisible. So this wasn't just solving a paradox, it was really setting the stage for a completely new kind of physics, where space itself was an active player. It really opened up the idea that the stuff between objects could be just as important, maybe even more important than the objects themselves.
Okay, so we've moved from Newton's discomfort, his spooky action, to Faraday's brilliant intuitive leap, visualizing these invisible fields. But intuition, while it's powerful, often needs a really solid mathematical framework to truly revolutionize science, right? And to offer precise predictions. And that's where James Clerk Maxwell steps onto the stage. A Scottish physicist, arguably one of the greatest theoretical physicists of all time, he basically translated Faraday's vision into the universal language of equations.
Maxwell's achievement, which he pulled off in the 1860s, was truly monumental, just incredible. He synthesized all known phenomena of electricity and magnetism, everything from static charges to magnetic currents, how they influenced each other, into a single, coherent theoretical framework. And he did this using a set of just 4 elegant differential equations. Maxwell's equations, we still call them. What's incredible is that these equations showed how changing electric fields could create magnetic fields, and crucially, how changing magnetic fields could create electric fields. It was this beautiful, self-sustaining dance between electricity and magnetism. This dynamic interplay meant that if you, say, wiggled an electric charge, that wiggle would generate a changing magnetic field, which in turn would generate a changing electric field, and so on, propagating outwards, like ripples in a pond, but, in 3 dimensions. But Maxwell's theory went far beyond just describing static forces, as you mentioned. His equations made an absolutely stunning prediction. They showed that a disturbance in this unified electromagnetic field, a ripple, if you will, would propagate outwards as a self-sustaining wave. And here's the fascinating part. When he calculated the speed of this predicted wave, using only constants derived from electrical and magnetic experiments, things you could measure in a lab, he arrived at a value that was stunningly, almost unbelievably close to the known speed of light.
Wow. That must have been an absolutely incredible aha moment. To realize that these seemingly separate ideas, electricity, magnetism, unified into this concept of a field, could actually predict something as fundamental as light itself. Were there any initial doubts? or resistances to such a radical idea at the time, especially since it meant, well, throwing out established concepts.
Oh, absolutely. Initially, there was definitely a mix of awe and skepticism. It was just so stunningly elegant, mathematically beautiful, and the precision with which it predicted the speed of light was really hard to ignore. But yes, it also meant discarding the long-held idea of a luminiferous ether, this hypothetical invisible medium that scientists thought light waves had to travel through, much like sound waves need air or water to travel. Maxwell's equations suggested that light didn't need any medium at all. It was a self-propagating disturbance of the electromagnetic field itself. And that was a significant conceptual hurdle for many physicists. It defied their mechanical intuition about waves. Yet, the evidence just became overwhelming over time. The conclusion was inescapable and absolutely revolutionary. Light itself was an electromagnetic wave, a vibration in this electromagnetic field. This was the moment the classical field really came of age. It wasn't just a mere bookkeeping device anymore, no longer just a conceptual aid. It became a dynamic, physical entity with its own reality. This field was capable of carrying energy, momentum, information across the cosmos. So if we connect this to the bigger picture, it means that when you see light, whether it's from the sun or your phone screen or a distant star, you're not seeing tiny little particles moving through space in the old sense. You're seeing a dynamic excitation, a ripple of the electromagnetic field that permeates space itself. And it also unified the entire electromagnetic spectrum, from radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. They're all just different frequencies, different wavelengths of vibrations in this one universal electromagnetic field. It's a profound shift from a particle view of light to a field view.
And this classical field theory, it reached its absolute peak with Albert Einstein's general theory of relativity in 1915. He took Maxwell's idea of fields and applied it to gravity, but with an even more mind-bending twist. Instead of gravity being a force in space, like Newton thought, or even like Maxwell's field in space, Einstein fundamentally changed space itself. This was a radical departure, even from Newton's brilliant description. Why did Einstein feel the need to go even further? Newton's gravity theory worked incredibly well, didn't it?
That's a great question, and it really gets to the core of Einstein's genius and the problems he saw. Newton's gravity, remember, was a theory of instantaneous action at a distance. If the sun suddenly vanished, poof. Newton's theory implied Earth would instantly fly off its orbit. Instantly. But Einstein's earlier special theory of relativity, published back in 1905, had already shown that nothing, not information, not forces, not even the effect of gravity, could travel faster than the speed of light. So this created a direct contradiction, a major problem. How could gravity act instantaneously if light itself had a speed limit? It just didn't add up. So where Maxwell's electromagnetic field existed in a static, absolute background of space and time like actors on a fixed stage, Einstein did something truly radical. He fused the gravitational field with spacetime itself. He didn't posit that mass and energy create a force field within space. Instead, he proposed that they literally curve and warp the very geometry of spacetime. That's the heart of general relativity. In this view, gravity is not a force that propagates from a distant object in the usual sense. It is the direct manifestation of this spacetime curvature. So, a planet orbiting the sun isn't being pulled by some invisible propagating force. It's simply following the straightest possible path, what physicists call a geodesic, through this curved spacetime.
Okay, so if I'm visualizing this right, it's kind of like imagining a bowling ball sitting on a stretched rubber sheet. It makes a big dip, right? And a marble rolling nearby isn't being pulled by the bowling ball directly. It's just following the contours of the warped sheet, its path bending as it moves through the dip. Is that a decent way to think about gravity in this context? It makes it feel less like a mysterious pull and more like, geometry in action.
That's a perfect analogy. It's one of the best ways to visualize it. The marble isn't being pulled by the bowling ball. It's just following the path of least resistance, the straightest line possible, through the curved geometry of the sheet. It's a fundamental shift from thinking about gravity as a force to thinking about it as geometry. And this means that here, with Einstein, the field, specifically what we call the gravitational field or the metric field, became the very fabric, the fundamental stage upon which all events unfold. It's no longer just a field in space. Rather, space itself, or more accurately, space-time, is the field. This really cemented the classical field as an absolutely fundamental component of reality. Not just an explanatory tool anymore, but the very canvas upon which the universe is painted. It definitely moved beyond being just a conceptual trick to being seen as physical reality.
Okay, so just when we thought we had reality pretty well mapped out, right, with these really elegant classical fields, Maxwell's equations handling light beautifully, Einstein's describing gravity as the curvature of space-time itself, And the turn of the 20th century threw some really serious curveballs. Phenomena started popping up in experiments that classical physics, no matter how elegant or precisely formulated, just couldn't explain. Where did the first cracks in this beautiful classical edifice start to show?
Precisely. Yeah, for a while there, classical physics seemed to have, well, almost all the answers. But then came what we now call the quantum revolution. Experiments looking at phenomena like black body radiation and also the photoelectric effect present an absolutely undeniable evidence that energy wasn't continuous, as classical fields would imply. You could think of classical fields like water flowing continuously from a tap, right? You could adjust the flow to any tiny amount you want, meaning energy could take basically any value smoothly. But these experiments suggested something different. They suggested that energy came in discrete packets, or quanta. For example, with black body radiation, that's the light emitted by hot objects, classical physics predicted that a hot object should emit an infinite amount of ultraviolet light, which obviously doesn't happen. It was called the ultraviolet catastrophe. The solution proposed by Max Planck around 1900 was revolutionary. Energy could only be emitted or absorbed in these discrete packets, these quanta, not continuous. Then came the photoelectric effect. That's where shining light on a metal can eject electrons. But it only worked if the light's frequency was above a certain threshold. Didn't matter how bright the light was below that. Classical wave theory couldn't explain this at all. It suggested brighter light should always eject electrons, regardless of frequency. Einstein explained this by proposing that light itself actually came in discrete packets of energy, what we now call photons. These shocking discoveries, they really forced the development of quantum mechanics and ultimately led to quantum field theory, or QFT. And QFT, they represent our most fundamental understanding of reality today.
That's a massive shift. So QFT took the classical concept of the field and just radically transformed it. This isn't just about making technical adjustments, is it? It sounds like a complete paradigm shift, a fundamental reimagining of existence itself. How did the scientific community even react to something so profoundly different from their established classical understanding? Must have been quite a shock.
Oh, it was definitely met with a mix of awe, confusion, and sometimes even outright resistance. Even from some of the very founders of quantum mechanics. Niels Bohr famously said something like, "Anyone who is not shocked by quantum theory has not understood it," which tells you something. And Einstein, despite his crucial role in explaining the photoelectric effect with photons, he famously struggled with many aspects of quantum mechanics later on, particularly its probabilistic nature. You know, his famous quote, "God does not play dice." Haffa. It was a monumental upheaval. It forced physicists to abandon many of their deeply ingrained classical intuitions about how the world worked, the differences between a classical field and a quantum field. They're so profound that they really do represent a complete schism in our conception of existence. It's kind of like going from believing the Earth is flat to understanding it's a sphere. It just changes everything about how you navigate and perceive your world.
So, okay, what does this all mean for us, for the listeners, and how we understand the basic building blocks of the universe? This seems like the most fundamental difference, and it's a big one. It truly challenges our everyday intuition. Think about how we normally perceive things smoothly, continuously, right? Classical fields work that way, allowing for any value in between. But quantum fields, they're different in a very, very profound way.
That's exactly right. Let's elaborate on the continuous nature of a classical field first, just to be clear. As you said, its amplitude, like the brightness of a light wave or the strength of a gravitational field, could, in principle, have any value at all. Its energy could be increased or decreased by any tiny infinitesimal amount, just like adjusting the flow of water from a tap. There's no smallest increment. It's like a smooth, continuous dial. You can have a tiny ripple, a slightly bigger ripple, or one infinitesimally different. By contrast, a quantum field is quantized. This is the absolute core distinction. It's fundamental. It means the field can only hold energy in discrete chunks, or quanta. Imagine it like the rungs of a ladder. You can be on rung 1 or rung 2 or rung 3, but you absolutely cannot hover infinitesimally between rung 1 and rung 2. It's just not allowed. The field's vibrations, its excitations, can only exist at specific allowed energy levels. So for the electromagnetic field, the smallest possible unit of excitation, the smallest chunk of light energy, is what we call a photon. A beam of light, therefore, isn't a continuous classical wave. It's actually a stream of these individual discrete quanta, these photons. A brighter beam of light simply has more photons hitting your eye per second. It's not that the waves themselves are somehow more energetic in the classical continuous sense, which is a common misconception. It's more like turning up the volume by adding more individual sound packets, if you could think of it that way, not by making existing waves louder continuously. And this principle, this quantization, it applies not just to fundamental forces like electromagnetism, but remarkably, it applies to matter itself. Everything at its most fundamental level comes in these discrete packets.
Wow. This is a huge shift from our everyday experience, isn't it? It means that at the most fundamental level, energy and even matter, they aren't smooth and infinitely divisible. It's almost like reality has a kind of pixelated quality to it at its deepest scales. Imagine trying to pour half a drop of water. You just can't do it. There's a minimum amount. This quantization implies a sort of fundamental granularity to reality, which is pretty mind-blowing when you really stop and think about it. And this inherent granularity, this chunkiness, it leads directly to the second profound difference. And this one truly dissolves a distinction we've held for centuries. I mean, going all the way back to ancient Greek philosophers debating what stuff was made of. That's the idea of particles versus fields. We've always thought of things as either little bits of stuff, discrete objects, or these diffuse influences that fill space. But QFT just blurs those lines entirely.
You're absolutely right. That distinction was fundamental in classical physics. You had particles like electrons or billiard balls seen as localized objects with definite positions and momenta, little things. And then you had fields, like the electromagnetic field, which were these diffuse entities that filled space, acting as the mediators of forces between the particles. These were two very different categories of existence. You either had a thing or an influence. But in quantum field theory, this distinction completely dissolves. It's just gone. It's a radical redefinition of what stuff actually is. The field is the underlying fundamental reality. That's the bedrock. What we perceive as a particle, like an electron, is nothing more than a localized, quantized excitation of its corresponding field. So, for instance, there isn't just an electron particle that exists somewhere as a tiny billiard ball waiting to be found. Instead, there's an electron field that permeates all of spacetime, everywhere, always, even when no particle electron is present. And what we measure to be an electron is simply a ripple, a specific vibration, a particular excited state in this electron field. It's a localized excitation carrying one quantum of energy and possessing all the specific properties we associate with an electron: its charge, its mass, its spin. If we dive a bit deeper into this, the universe, in this quantum field view, is not a collection of tiny solid billiard balls bouncing around. That's the old picture. Instead, it's a vast, interconnected set of fundamental interacting quantum fields, and the particles we observe and interact with, electrons, protons, photons, quarks, you name it, they are merely the ephemeral vibrations or excitations of these underlying fields. It's kind of like the universe is a symphony, maybe? And the particles are just the notes being played by the instruments, where the instruments are the fields themselves. And this framework elegantly explains phenomena that are completely impossible in classical physics, like particle creation and annihilation. In QFT, energy in one field, say the photon field, light, can be converted into excitations in other fields. For example, creating an electron and its antiparticle, a positron, out of pure energy, like from a high-energy gamma ray. It's literally the field giving birth to what we call particles, and then absorbing them back again under the right conditions.
That's a fantastic way to put it. Yeah, like the universe is a symphony where the fields are the instruments playing the notes that are the particles. So it's not like the particles are floating on the field. The particles are the field, just in a certain excited state. If you get that pond analogy again. In the classical view, you'd have the water as the field, and then ducks swimming on it as the particles. Separate things. But in quantum field theory, there's just the water. The field is the fundamental thing. The ducks are just specific localized ripples or disturbances in the water itself. The water itself is the duck when it ripples in that certain characteristic way. Does this dissolution of the particle field distinction, does it have any philosophical implications for how we perceive the solidity of matter? Or maybe the emptiness of space?
Oh, it absolutely does, and they're quite profound, really. It means that what we perceive as solid matter is fundamentally ephemeral. It's not made of tiny, unchanging, hard little bits in the way we might intuitively think. Your hand, your desk, the stars, they are incredibly stable, yes, but ultimately they are persistent patterns of excitation in these underlying fields. Intricate dances. And empty space isn't truly empty because these fields are everywhere, permeating everything, even in their lowest energy state, the vacuum state. So it completely reframes our intuitive understanding of substance and void. It suggests a deeper, unified reality where everything is just a manifestation of these vibrating fields. It's not just a scientific model, it's really a new way to contemplate what reality is.
And that leads perfectly to maybe the most mind-bending difference of all. And this is one that really makes you rethink everything. It concerns something we usually think of as absolutely nothing: empty space, the vacuum. You strip away all the matter, all the radiation, and you're left with, well, nothing, right? So classical physics told us. The ultimate void, utterly inert, still.
That's exactly it. In classical physics, a vacuum is truly completely empty. If you could somehow remove every single particle, every bit of radiation, every last trace of energy, then the fields, like the electromagnetic field, would simply have a value of 0 everywhere, a flat line. It would be a state of absolute nothingness, inert, perfectly quiescent. There'd be no activity, no hidden potential, just a serene, unchanging void. However, the quantum vacuum is a starkly, almost unbelievably different place. This is where the Heisenberg uncertainty principle comes back into play, and when you apply it to fields, it dictates something really weird. It says that a field cannot simultaneously have a precise value, like exactly 0, and a precise rate of change, like 0 change, meaning static, across all points in space. It's a bit like trying to perfectly pinpoint both the exact position and the exact momentum of a particle at the same time. The quantum world just doesn't allow for that kind of absolute certainty or stillness. And as a direct result of this principle, every single quantum field is constantly undergoing these minute, spontaneous fluctuations. Even in its very lowest energy state, which is what we call the vacuum, it's never truly still. This constant background buzzing activity in the vacuum is often described, maybe poetically, as a quantum foam. It's like a seething cauldron of virtual particles that are constantly popping into existence and then vanishing back out of existence for incredibly fleeting moments. They effectively borrow energy from the vacuum for a tiny fraction of a second, a time allowed by the uncertainty principle, and then they have to disappear back into it almost instantly. Now, it's really crucial to understand these are not real particles in the sense that we can directly observe them hanging around or that they exist permanently. They are transient, ephemeral disturbances, sort of like the static you might see on an old television that isn't tuned to a channel, just background noise.
Yeah.
But their transient existence has very real, memorable effects. And this isn't just speculation either. It's not just theoretical fancy. The effects of these vacuum fluctuations have been confirmed through incredibly precise experiments. For instance, there's the Casimir effect. If you place two uncharged parallel metal plates very close together in a vacuum, they actually get pushed together. Why? Because the virtual particles popping in and out of existence are slightly restricted between the plates compared to outside, creating a tiny pressure difference that pushes them together. It's the vacuum energy doing the pushing. Another crucial example is called the Lamb shift. This is a tiny, unexpected shift in the energy levels of the hydrogen atom. It couldn't be explained by older theories, but QFT predicts it precisely as being due to the interaction of the electron with these very vacuum fluctuations. The electron is constantly jostled by these virtual particles. These effects are minuscule, yes, but they are undeniably real. They demonstrate that the vacuum is anything but empty. So the profound impact of all this is that the quantum vacuum is not empty. It's far, far from it. It is a dynamic, energetic medium. It's the fertile ground from which all reality, including all the particles we observe, actually emerges. This fundamentally changes our understanding of nothingness. It transforms it from a void into a vibrant plenum, a buzzing sea of potential energy and activity.
Wow. Okay, this raises a really important question then. If what we perceive as empty space is actually buzzing with this activity, this quantum foam of particles popping in and out of existence, and these virtual particles have actual measurable effects, what does that mean for how we think about the very foundation of the universe? It suggests that nothing is actually something pretty dynamic, and maybe everything we do see is just a slightly more stable, longer-lasting ripple in this underlying sea of potential. Could this vacuum energy even play a role in some of the larger cosmic mysteries out there, like, say, the expansion of the universe or maybe dark energy?
That's a very insightful question, and yeah, it touches on some of the biggest open problems in physics today.
Absolutely. The idea that the vacuum itself possesses energy, as quantum field theory implies, is indeed fascinating when we look at cosmology at the universe on the largest scales. There's this concept known as dark energy, which, as you mentioned, is currently the leading explanation for why the expansion of our universe is actually accelerating, not slowing down. And one of the prime candidates for what dark energy might be is, in fact, the energy of the quantum vacuum. It seems like a natural fit, right? Empty space having energy that pushes things apart. However, there's a huge problem, a really huge one. When physicists try to calculate the expected energy density of the quantum vacuum based on QFT, the number they get is enormously larger, I mean, by many, many orders of magnitude, like 120 orders of magnitude larger than the amount of dark energy we actually observe driving the cosmic acceleration. This is one of the greatest unsolved puzzles in physics. It's often called the cosmological constant problem. It's a major headache.
So while the quantum vacuum is definitely active and has energy, understanding its full cosmological implications, why there is this massive discrepancy, well, that remains a huge frontier of research. It suggests that even our most fundamental understanding, QFT, might still be incomplete, or we're missing a crucial piece of the puzzle.
So what does this all mean for us, really, as we wrap up this journey? The journey of the field concept is just an incredible testament to the power of human scientific inquiry, isn't it? An abstraction. It's an idea that evolved and reshaped our understanding of reality time and time again, constantly pushing the boundaries of human thought.
Absolutely. Think about the arc we've traced. It began as this clever, almost philosophical way to demystify Newton's spooky action at a distance. A crucial conceptual leap just to make sense of gravity without direct contact. Then it blossomed into the dynamic, verifiable reality of Maxwell's electromagnetism, where light itself was revealed as a vibration of this field, uniting electricity, magnetism, and optics. And it reached a kind of classical apex when it became the very geometry of spacetime in Einstein's hands, fundamentally redefining gravity not as a force, but as the curvature of the cosmos itself. Yet its transformation into the quantum field marked the most radical shift of all, forcing us to completely rethink the very nature of matter, energy, and even empty space. So, to summarize the key takeaways for you, the listener, the classical field, think of it as a deterministic, continuous backdrop, a smooth stage upon which a world of solid, distinct particles played out their interactions. It was predictable, continuous. In stark contrast, the quantum field is a probabilistic, quantized foundation, and particles don't just exist on it. They emerge as mere excitations of it, like notes emerging from an instrument. It's inherently fuzzy and granular. It takes what we thought of as a void, the vacuum, and transforms it into this dynamic, seething plenum, a sea of infinite potential, constantly bubbling with virtual activity. And ultimately, the quantum field unifies what we once considered two totally separate categories, matter and force, under a single profound principle. Everything you see, touch, and feel is, at its absolute core, just a manifestation of these underlying quantum fields doing their dance. In understanding this astonishing evolution from classical to quantum fields, we don't just learn the history of a scientific idea. It's more than that. We trace the very contours of humanity's deepening and, frankly, ever more surprising understanding of the fundamental nature of the universe itself. It's an incredible story of how science continuously refines, challenges, and transforms our very perception of reality. It shows us that what we think of as solid things and empty space are actually much more complex, much more dynamic, and much more interconnected than we could ever possibly imagine just using our everyday intuition.
This journey really makes you think, doesn't it? It leaves you with some deep questions. Like at everything we perceive as a solid particle, an electron, a proton, even you, right? As a collection of countless intricate patterns of these particles is ultimately just a fleeting vibration, an excitation of a fundamental field that permeates all of reality. Does that change your perspective on existence? What does it mean for our understanding of identity, maybe, our sense of self? If we are all just incredibly complex and organized patterns of ripples in some underlying cosmic ocean, this concept of the quantum field, it doesn't just explain the universe in a scientific way. It really reshapes our very understanding of existence. It invites you to look at the world around you, even seemingly empty space, with a totally newfound sense of wonder, and maybe a deeper appreciation for the hidden, intricate dance of fields and excitations that makes up absolutely everything. Keep exploring, keep questioning, and keep diving deep.